Assalamu alaikum and peace be upon you. Today we'll be solving Cambridge O-Level Physics past paper. This is paper 2 variant 1 from October-November 2024. Now we have 1 hour and 45 minutes to solve this paper, but I'll be showing you how to complete this entire paper as fast as possible and still have time to recheck your answers. So the total mark for this paper is 80. And we will be taking the acceleration of gravity to be 9.8 meter per second square. Question 1. A trolley of mass 0.2 kg is at rest on a frictionless surface. A block of wood is attached to the trolley. The volume of the block of wood is 0.0012 cubic meter and the density of the wood is 650 kg per cubic meter. Question A. Calculate the combined mass of the trolley and the block. So we already have the mass of the trolley, which is 0.2 kg. Now to find the mass of the block, we're going to multiply the volume and the density of the block of wood. So 0.0012 multiplied by 650 is 7.8 kg. So the total mass is 7.8 plus 0.2, that is 8 kg. Question B. Figure 1.1 shows that a student attaches a spring of spring constant 14 Newton per meter to the front of the trolley. The student holds the trolley and the block and stretches the spring. He releases the trolley of the block and the block. The trolley and block accelerates from rest. As the trolley and block accelerate, the student keeps the extension of the spring at 0.035 meter. Calculate the force exerted by the spring on the trolley. So we have the extension and we also have the spring constant. So the force is equal to kx, where k is the spring constant and x is the acceleration. So 0.035 multiplied by 14, that will be 0.49 Newton. So 0.49 Newton is the answer. The trolley and block are pulled a distance of 0.86 meter by the spring. Calculate the work done on the trolley. Now the work done is nothing but force multiplied by distance. We already calculated the force here. So to get the work done, we will be multiplying 0.49 with 0.86. And we will get 0.42 joule, which is the work done. Explain why the power transfer to the trolley and block increases as the speed increases. So when the speed is increasing, the force is also increasing and the acceleration is also increasing, as force is equal to mass multiplied by acceleration. So the work done is also increasing, and since the work done is increasing, the energy transferred per unit time is increasing. So that means the power will also increase. So for 2 marks, we can just write the increase in speed means the force and the work done increases per unit time. So the power also increases. Now let's move on to question 2. A student makes a ball from modeling clay. The ball has a mass of 0.2 kg. She drops the ball from a height of 40 meter above the ground. Question A, Roman 1. Calculate the initial gravitational potential energy of the ball. So this is pretty easy. We know that gravitational potential energy is equal to mgh. So mass is 0.2, gravity is 9.8 and height is 40 meter, which makes the gravitational potential energy into 78.4 joules. Roman 2. Calculate the speed of the ball immediately before the ball hits the ground. Ignore the effect of air resistance. So since we are ignoring the effect of air resistance, we will consider all of the gravitational potential energy has converted to kinetic energy. So 78.4 is equal to half mv square, which will make v is equal to 28. So the speed is 28 meter per second, just before the ball hits the ground. Question B. When the ball hits the ground, it stops moving. The kinetic energy of the ball is transferred to internal energy. The temperature of the ball increases. Roman 1. The specific heat capacity of modeling clay is 1400 joule per kg per degree Celsius. Calculate the maximum possible temperature increase of the ball. Show your working. So we have the specific heat capacity, we have the mass of the ball, and we already calculate the total energy of the ball to be 78.4. So we can use this formula, E is equal to mc del theta, where theta is the temperature change. So 78.4 is equal to 0.2 multiplied by 1400 multiplied by del theta. Using that, we will see that del theta is equal to 0.2814 degrees Celsius. So we can convert it into 2 decimal places. 0.28 degrees Celsius is the answer. Roman 2. Suggest one reason why the actual temperature increase of the ball may be smaller than the value calculated in question B, Roman 1. So in our previous calculation, we assumed that the entire energy of the ball will be converted into internal energy. But that is not true for real-world cases. And that's because some energy will be lost as sound when the ball falls on the ground. And also, we ignored the effect of air resistance, which is not possible in real-world scenarios. So some energy is lost due to air resistance and some energy is lost as sound energy. And that is why the actual temperature increase might be smaller. Okay, question 3. Figure 3.1 shows gas at room temperature. The gas is trapped in a metal cylinder by a metal piston fixed in position. The metal cylinder is immersed in boiling water and the temperature of the trapped gas increases. Question A. Explain in terms of electrons and the atoms of the metal how thermal energy is transferred through the walls of the metal cylinder. So this question is from the chapter Energy Transfer. And the process that is happening in here is conduction, specifically conduction in a metal where free electrons are the main reason why the metal is heating up. So we can write it as particles vibrate more due to the gain in temperature, and thus free electrons move through the metal and collide with neighboring electrons and atoms. And when this happens, they transfer heat energy to those neighboring particles. Therefore, energy is transferred fast by conduction. And that's enough for 3 marks. Question B. The piston is fixed in position, so the pressure of the gas increases as the temperature of the gas increases. Roman 1. State what happens to the motion of the particles of the gas as the temperature increases. So this is easy. The particles will gain kinetic energy and move faster. And since this is only for 1 mark, we don't have to go into the details. Okay, Roman 2. Explain in terms of the particles of the gas why the pressure the gas exerts on the walls of the metal container increases as the temperature increases. So the pressure of the gas is force per unit area exerted when the particles collide with the walls of the container and when they collide with each other. When the particles gain kinetic energy, the particles collide with each other and the walls more often and they exert greater force. Therefore, the pressure of the gas increases. Question C. The gas in the cylinder reaches a temperature of 100 degrees Celsius. The piston is released and moves to the right. The temperature remains at 100 degrees Celsius. The pressure of the gas now decreases. Roman 1. Explain in terms of the particles of the gas why the pressure of the gas now decreases. So since the piston is moving to the right, it means the volume inside of the container will increase. So the pressure decreases as the particles are further apart, so there is less chance of collision with each other and with the wall per unit time. Roman 2. Eventually the piston stops moving. Explain why. So the piston will stop moving when the pressure inside of the gas container is equal to the atmospheric pressure. So there will be no resultant force acting on the piston, so it will stop moving. Okay, question 4. A student directs a beam of white light from a filament lamp towards a glass prism in a dark room. Figure 4.1 shows the beam of white light incident on the left-hand side of the glass prism. A screen is placed to the right of the glass prism. Red light is observed at point R on the screen and violet light is observed at point V. Question A. Draw on figure 4.1 to show the paths of the red light and the violet light between the left-hand side of the prism and the screen at point R and point V. So this question is from dispersion of light, and we know that when light moves into a glass prism, it will split into 7 different colors. And in here, when the light is moving from air into the glass prism, it is moving from less dense to more dense. So it will move towards the normal. And when it moves from the glass prism into the air again, it will move from more dense to less dense, and it will move away from the normal. And the points where R and V are shown are already given here, so we will connect them just like this. And that's enough for 2 marks. Question B. State what these observations show about the change in speed of red light and the change in speed of violet light as each enters the glass from the air. Okay. From what we drew, we can see that violet light is bending more than red light, which means both violet and red light will have their speeds decrease as they enter the glass from the air. But red light will still have more speed than violet light. So that is why red light is bending less than violet. Question C. 5 other colors of light appear on the screen between the red light at point R and the violet light at point V. Roman 1. State the names of the 5 colors and list them in the correct order from red to violet. So this is easy, just use Roig Biv. So red, comma orange, comma yellow, comma green, comma blue, comma indigo, comma violet. So the 5 colors in order are red, orange, yellow, green, blue, indigo, and violet. Roman 2. State how the frequency and the wavelength of the colored light change going from red to violet. So from red to violet, we know that the frequency will increase and the wavelength will decrease. Question D. On figure 4.1, point P is shown immediately next to point R. No light is observed at point P, but a detector at point P registers radiation reaching the detector. State which region of the electromagnetic spectrum is detected at point P. So from Ramin-Vukska, we know that the region of the electromagnetic spectrum just before visible light is infrared. And this is infrared radiation. So that's why radiation is being registered on the detector. Question 5. Ultrasound is a longitudinal wave which cannot be heard by humans as the frequency of ultrasound is too high. Question A. Ultrasound waves cannot travel in a vacuum. Explain why. So we know that ultrasound travels by vibrating particles to move forward. And since there are no particles in a vacuum, ultrasound cannot travel through a vacuum. Question B. Describe how a longitudinal wave differs from a transverse wave. So we are given 2 marks for this. So we can just write longitudinal wave vibrates particles parallel to the propagation direction, while transverse waves vibrate the particles perpendicular to the propagation direction. And that's it. Question C. An ultrasound transmitter used for a medical scan produces an ultrasound wave of frequency 8.4 MHz. In soft human tissue, ultrasound travel as 1500 meter per second. Roman 1. Calculate the wavelength of this ultrasound wave in soft tissue. So we know that the wave equation is V is equal to F lambda, where V is the speed, F is the frequency, and lambda is the wavelength. Therefore, lambda is equal to V divided by F. Lambda is equal to 1500 divided by 8.4 into 10 to the power 6 Hertz. Therefore, the wavelength is 1.79 into 10 to the power minus 3 meter. Roman 2. The ultrasound wave passes from the soft tissue into bone where the speed of ultrasound is greater than 1500 meter per second. State what happens to the frequency and to the wavelength of the ultrasound wave as it passes into the bone. So this is important. The frequency will remain constant because the frequency solely depends on the source of the waves. And from the wave equation V is equal to F lambda, we can see that when the velocity increases, the wavelength will also increase. Therefore, the frequency will remain constant and the wavelength will increase. Okay, question 6. A bar magnet can rotate freely around a thin rod through its center. The bar magnet is at rest on a frictionless horizontal surface in a laboratory which is shielded from the Earth's magnetic field. Question A. State a substance from which the bar magnet could be made. So the answer is steel because most magnets are made out of steel, as steel retains its magnetism for a long period of time. Okay, question B. The thin rod is perpendicular to the top and bottom surfaces of the bar magnet. Figure 6.1 shows a view from above of the magnet with the north pole, the south pole, and the thin rod labeled. Draw on figure 6.1 to show the pattern and the direction of the magnetic field around the bar magnet. So this is a very easy question. We know that the direction of the magnetic field is from the north pole into the south pole. And this is how it is drawn. Question C. An electromagnet is switched on and a strong magnetic field is created around the bar magnet. Figure 6.2 shows the direction of the strong magnetic field due to the electromagnet from left to right across the page. Roman 1. Draw arrows on figure 6.2 to show the direction of the horizontal forces that act on the poles of the bar magnet. So let me explain what exactly is happening over here. When you put the bar magnet inside the magnetic field lines of an electromagnet, the bar magnet is actually going to turn so that the magnetic field lines will be going out of the north pole into the south pole. And the bar magnet will become parallel to the magnetic field lines. So this bar magnet is going to rotate anti-clockwise. So we will be drawing our arrows like this. Roman 2. Describe and explain what happens to the bar magnet when the electromagnet is switched on. So we can write a turning force or a torque is produced due to the interactions of both magnetic fields of the electromagnet and the bar magnet, which rotates the magnet. The magnet rotates until it is parallel to the field lines. Question 7. A filament lamp connected to a 12-volt power supply transfers 24 watt of power. Question A. Calculate Roman 1 the current in the lamp. So we know that power is equal to current multiplied by voltage. So we have the power and we have the voltage. So the current is power divided by voltage. 24 divided by 12 is 2. So 2 ampere is the current. Roman 2. The resistance of the lamp in this circuit. So the formula for resistance is voltage divided by current. Therefore 12 divided by 2 is equal to 6 ohm. So the resistance is 6 ohms. Question B. A student has a battery of electromotive force 12 volt. The student uses the battery in a circuit with the 12-volt filament lamp to obtain a range of suitable readings and plots the current voltage graph for the lamp. Roman 1. Figure 7.1 shows the battery and the filament lamp. On figure 7.1, complete the circuit diagram of a suitable circuit. You will need to add additional components. So since we are plotting the current voltage graph, we will need to measure the current and the voltage. And another thing you need is a variable resistor, so you can vary the resistance and plot the graph for all of the different current and voltage measurements you get. So in this circuit we will need a variable resistor, an ammeter and a voltmeter. Now the resistor and the ammeter are connected in series and the voltmeter is connected parallel to the bulb. So we will draw it just like this. Roman 2. On figure 7.2, draw the shape of the current voltage graph for the filament lamp. So first of all, the current voltage graph will have a constant gradient which starts from the origin. And then eventually the gradient will keep on decreasing like this. And this will be the shape of the current voltage graph. Roman 3. State what happens to the resistance of a filament lamp as the applied voltage increases and explain one reason for this happening. So the resistance will increase, and this is because the increasing voltage leads to increasing temperature in the circuit. And the particles will vibrate more vigorously, which will impede electron flow. Question 8. The nuclide notation for the radioactive isotope hydrogen-3 is H31. Question A. Explain why hydrogen-3 cannot decay by the emission of alpha particles. So we know that for alpha particles, the nucleon number is 4 and the proton number is 2. So we can write the nucleus of hydrogen-3 only has 1 proton and 3 nucleons, which is not enough for the emission of alpha particles. Question B. Hydrogen-3 decays by the emission of beta particles to an isotope of a different element. This element is represented by the equation by Q. Roman 1. Complete the nuclide equation for the decay of hydrogen-3. So we know that beta particles have nucleon number 0 and proton number -1. And when we balance this equation, we see that 3 minus 0 is equal to 3 and 1 minus -1 is equal to 2. So Q will have nucleon number 3 and proton number 2. Roman 2. State the name of the element represented by Q. So the element with proton number 2 is helium. So the answer is helium. Question C. The half-life of hydrogen 3 is 12 years. Roman 1. Define half-life. So the half-life is the time taken for the number of atoms to become half. So the keywords here are time and half. Roman 2. A sample of hydrogen 3 is placed on a laboratory bench next to a Geiger-Müller tube and counter. The count rate is recorded at the same time on 4 successive days. Table 8.1 shows the count rates obtained. State why the count rate decreases and then increases. So the answer is, due to the spontaneous or random nature of decay, the count rate will increase or decrease randomly. Okay, let's move on to the last question, question 9. A stable star in a distant galaxy has a mass that is more than 15 times the mass of the Sun. Question A, Roman 1. State the name of the nuclear reaction that occurs at the center of the star and describe this nuclear reaction. So similar to the Sun, the nuclear reaction will be nuclear fusion. And in here, 2 or more hydrogen nucleus joins together to form a large nucleus of helium. Roman 2. Explain how this nuclear reaction helps to keep the star stable. So the reason is, when a lot of thermal energy is produced, it produces a very high pressure, and this pressure balances the inward gravitational force of the star. So we can write the transfer of thermal energy produces high pressure and the inward gravitational force is balanced due to it. Question B. As a massive star approaches the end of its life, it stops being stable and becomes a red supergiant. Roman 1. State why the nuclear reaction can no longer keep the star stable. So the reason is, there is not enough hydrogen left in the star to carry out nuclear fusion. Okay. Roman 2. Describe what then happens to the red supergiant. And this question is for 3 marks, and you need to remember this sequence of events. So at first, the red supergiant will explode, and then it will turn into a supernova. And then it will produce heavy elements to form a nebula, and then it will eventually leave behind a black hole. So this sequence is very important, and this is an important question. So with this, we have solved all 9 questions of the past paper. And if you answer your O-level question paper like this, you will have plenty of time to recheck and make sure you didn't skip any steps or make any silly mistakes. So best of luck for your exams, and let me know which past paper I should tackle next.